So that's a little bit about what we're doing globally. Now this week, we're here to talk about parametric design, which a lot of you know looks like this. If we could, can we turn the light on real quick? So for me, I like to start these types of seminars by stressing one thing. This is a tool. It doesn't replace anything that you do. It doesn't replace you. It helps you. It's an extension of your engineering mind. That's all it is. And at the end of the day, it will not replace you with a piece of paper and a pen in your hand. So that's why I always like to start off and just know that every single one of the scripts that you're going to do is going to start on a piece of paper. If you're not doing it that way, I've been using it for 4 years. Every single one of my scripts that I start, it starts on paper. So if I try and do it without it, I can maybe do a good job, but it's not even comparable if you're not using a piece of paper. It doesn't replace your mind, remember that. So I have this little principle I made up. That I started when I first started doing Grasshopper 4 years ago. Programming equals geometry, geometry equals programming. The cool thing about our industry is we actually deliver things that are in 3D, so it really behooves us to be able to work in 3D, to be able to understand things in 3D and set them out that way. The geometry part is the important part. And right now, we have a lot of different ways. You can use a pen and paper, you can use CAD, you can use Revit, or now you can use programming to define the geometry. And therein lies the word right there that scares people when it shouldn't. Because this programming is what unlocks so much more for you. If you're able to programmatically define your geometry, and a lot of this is able to be programmatically defined, you find yourself much more powerful than you did before. And you'll see that going forward. The key is, behind all of this, is that you understand my geometry has to go through programming. And for it to go through programming, we don't have artificial intelligence, which is good, because if we did, we might all be out of jobs. We need to be able to break it down in a way that the computer can help us do our jobs, not do our jobs for us. Okay? So the example that I always like to start off with, because it's a very simple, intuitive example, we're not going to do anything that's structure specific, just geometrically. Just going to talk about geometry, because that relates to everybody. And then I'm hoping that everybody starts to get ideas for how this stuff affects you and your specific discipline. Like I said, I'm structures, so it's easy for me to come up here and blab on about structures, but the MEP people and the technicians might not really get that as much. So like I said, you sit there and you say, what's my problem? So let's take on the problem of drawing an arc. Now, every single one of you, if I ask you to come up here and draw an arc, it's that simple with a pen and paper, right? It's something that and nothing will ever replace that either. If I was a good drawer, we'd actually come up here and we'd do all these kind of sort of Norman Foster type sketches, and it'd look beautiful. Nothing's going to replace that, all right? That's the good news. But the bad news is our industry, we're designers, designing is iteration. Things change, we work with other people all the time. Things are always in a constant state of limbo. Even until it's actually built and occupied, you're probably going to be asked to make changes. And we see this all the time. We have to make a change, and even though I came in here and I made this beautiful arc, if now we coordinate with somebody and we say, oh, actually the arc needs to be something like this now, I literally had to come in there and I had to draw it again. And you say, Emilio, it took you 2 seconds to do that. But you know what I mean. It's the issue of the multiplication of what is 5 minutes. You do that 20 times, that starts to become a significant part of your day. It's just trying to roll with the punches. I like to call it like design friction. It's just the stuff that, oh, we got to roll with the punches on this. We just lost a couple days because they moved this 2 millimeters. But it is what we have to deal with. Now, I don't know why it keeps doing this. The key behind this example is, let's try and define an arc by parameters so we can program it. And this is the important part. When you are sitting here at the beginning, you need to think, what is it that I'm trying to define? And a lot of you know, mathematics says we can define these lines. There's an infinite amount of ways to do it. I mean, I'm just randomly sort of drawing right now, but there's math behind all that. And you need to be able to break it down to something that a computer can understand. So anybody have any ideas on what we could do? tissue.
Start and end point.
Start and end point. Brilliant. Thank you. Start and end point. And I recommend that when you do it, you use multiple colors. Let's say input is red, output is blue. So start point, end point. That's part of it. Anybody else?
Curvature radius.
Curvature radius. Okay.
Number of center of radius.
Number of points. Center of. Anything else? Anybody going to be a real nerd and say polynomial equation or something like that? It could be something like x squared plus yx plus c or something like that, right? Well, maybe I'm too much of a nerd. But in what you guys have just shouted out there, that's not enough, that's too much. That's still taking me and drawing random lines, the infinite amount of possibilities there. There's still an infinite amount of possibilities here. So we need to pick one. I would say, we can pick any of them, but just because I'm ready to do this one. 3 points. 3 points defines an arc, right? We can figure out some sort of line that goes through that. And intuitively, I know that there's a tool in there that will take 3 points and figure out the radius and everything for us, okay? So that's cheating a bit, but that's why it's important to get your feet wet, because it's sort of like a self-fulfilling prophecy. The more you use Grasshopper, the more you know about it, the more you're able to sit down at this table and actually say, I can already foresee my last component is going to draw it for me, and it requires 3 points. So, we know right away, we want a 3-point arc, we better have a third point up there somewhere. So right now, those are our parameters. Is that enough? Is that really enough for us to do it? We need some other information. What other information? You need a plane. What else? I would say we probably need the setting out of all these points, right? So we need 3 sets of x, y, and z. So x1, y1, z1, you get the point, right? All right, so what I would propose, we know that we're hoping to roll with the punches, right? Could we just input 9 values there? The answer is yes. It's a computer, of course. We can just type in x1, y1, z1, all of them. Is that parametric? Yes. Is that convenient? No. Because every time something changes, you have to play mental gymnastics to actually say, I wonder what it actually means to move point 2 to y equals 5 or something like that. It's not very convenient. So what else can we do? Remember, our output is that. So we're drawing this picture, we're thinking our end game is this. And how do I break that down into something that a computer can understand? And this is the really important part of all of this stuff, is the sacrificial geometry. All of this jazz over here is just sacrificial. We're creating 3 points to create this curve. We've got 2 parameters in here. Most of the definitions you will come up with will have more than this, actually. And it's just the amount of steps that you go through. And we can walk through examples later in the week of examples where you create so much line work just to come out with something simple. But the main benefit is once it's done forever, and you can roll with the punches a lot quicker. So let's take this as the basis of our example here, and let's do it in Grasshopper. Before we start, I want to stress, this week we are going to try and do as much as possible without being too confusing. We're going to use Grasshopper first, then Dynamo. Dynamo is going to be really important for those of you using Revit a lot. But I go to Grasshopper first because I still submit that Grasshopper is a better way to learn. Dynamo is very new. It has things that I just consider to be bugs. Like they're just buggy things. Last week I saved a file, I opened it back up, and all my, they're called groups, were disappeared. It was gone. And to me, that's just a little bit unstable. Doesn't mean you can't learn from it. It doesn't mean it's not a good tool. Just know, if you're starting from scratch, you're probably going to have less headwind if you're using Grasshopper. Okay, so we'll start with Grasshopper this week. So, remember our principle. What was the principle that we started off with? Programming equals geometry, and geometry equals programming. So on the screen right here, what you're seeing is those two things in software form. Geometry, as you guys all know it right now, CAD, and programming over here on the right. And most of you know this already. The programming is not something that, ooh, scary, scary, scary kind of programming type of thing. It's actually pretty easy to learn. There's something called visual programming. And just to show you how easy I think, I would submit that this is, I made this little thing a long time ago. So, if you wanted to learn basic parametric scripting, I believe it would take you 2 to 3 days of just sort of knocking it on. Not even full days, just playing with it. And by the end of this course, I would expect that at least most of you would be probably here. Okay. Just to give you an example. And the 60% means you're 60% fluent. You're gaining 60% of the sort of benefits of being a parametric designer rather than just a normal designer. I say conservatively, it takes you another 5 or 6 days to go to the data tree structures, which really puts everything that we're going to talk about on steroids. We're going to cover that tomorrow. If you can get data tree structures down, you are, in my opinion, dangerous. You now can use parametric software inside out, and you are able to really put the hurtin on some modeling. And you could actually probably, arguably, be replacing the efforts of someone else. You could probably do something in minutes that takes someone else a day. There are examples of this. The next level up is the stuff people get scared of, but it doesn't apply to everybody. Basic, Visual Basic, C#, even Dynamo Studio scripting. Stuff like for loops, while loops, all these things that people go, oh, I can't do that, I can't do that. But yeah, no one really likes that. We're designers, we don't like to deal with that stuff. But that's not the stuff that you'll be dealing with in most cases with parametric design. And then finally, there's the advanced scripting, the nerd level. These are proper programming techniques. This is stuff like VHOM, which we will talk about. But just remember, to actually contribute to the VHOM really does require a lot of programmatic background, proper programming. So before you get scared at this new tool that we're going to introduce, just remember, that's the background. And remember, this, I always tell people, this one right here is the important part to get to. Data tree structures is important. But it's not hard to get to, and it's almost like, I speak Italian. Anybody else here speak Italian? That's right. If I got up on the board right now and I taught you 10 words in Italian and you could go live in Rome, all of you, that's what learning this stuff is like. It's that much of an impact for that little of an effort. It doesn't take that long to get down. All right, let's do it. Any questions so far? Now's the boring part. You get to do the tutorial. Okay. Most of you, I'm hoping, are at this level already, having worked with Vmol on the Nick Sensky stuff and other things. But just so we're all on the same page, I'm going to start working with lists here. Programming over here, geometry over here. I would say, let's start by creating some geometry. There's a point. And what am I going to do with that point now? Go back to my thing over here. Let's say I just created that point. I need to create, let's say, a second point that's a distance away from it along the, let's say, x-axis. Let's make programming equal geometry. So if I come over here, I double-click the canvas. Most of you know this already. You can type out commands. And you can make information jump across the media via right-clicking, and you go set one point. Boom. If you haven't been introduced already, green mode and red mode up here, very important. If you click on something and you're in red mode, it turns green. Everybody see that? It's very important. And if you're in green mode, the only things you see are green when you select them. And right now what it's telling us is we have a green point out here. This is a programmatic point. We can play on this in programmatic land. So for the rest of this example, we're not going to touch Rhino. We're just going to draw it using algorithms. So we want to create this, and we already got point 1 there. How do we get to point 2? It's distance a away. Anybody have any ideas what we can do?
Numbers.
Sorry?
Numbers, right?
Number slider. It's going to involve a number slider, but what's the, to make one sacrificial geometry out of that? How do I do it?
We can move the point.
Move the point. How you doing? All right, so we double click, we go move, that's nice. Now, for those of you who aren't familiar yet, every one of these little batteries, it's going to have an input and output. It always tells you what it does. Translate or move a point along an object or along a vector. Base geometry, translation vector. Base geometry, sounds like we should put the point in there. Translation vector right now, it's moving it 10 millimeters in the Z direction. So we can't even see it because we're looking at the XY plane here. What can we do? Probably, yeah, put a vector in there. That makes sense for us. Ah, we've done it. And then where's my number slider go?
Behind X.
Sorry?
Behind unit X.
Right here, right? F.
Yeah.
Uh-oh, where is it? It's far away. And then, those of you who haven't done your homework yet, I really feel, I'm happy for you because you still get this awesome feeling of the first time you play with a slider. You go, ooh, ah. It never stops being fun. So, okay, great. So that's second point. All right, crushing it. All right, anybody have any ideas on point 3 up there, the apex of our curve? How do we do that?
Moving at the same command.
Moving it in Y. Which point?
Same number slider in Y.
Sorry? Sorry?
Move it in Y, we can give different vector actually.
Give it a different direction. So which points am I going to move here? I got 2 points, right? And actually, I probably should have drawn this a little bit better. Because if I move either of those ones right now, in the Y or any direction really, you get something like over here, right? We kind of know that just by looking at it. So really what we probably want is,
We can use 2 vectors.
we can do 2 vectors, but trying to keep it minimal parameters because we don't want it to be too crazy, like we don't want to have to work too hard. What if we just stick with the 2 vectors we have? What does it inherently mean? What sacrificial geometry could we create such that this is maintained? A over 2. So that it's centered on these 2 points. Any ideas? So that it is at the middle of those 2 points.
It's the line.
There you go. So, like I said, sacrificial geometry, you can be thinking, I need to get to the midpoint of those 2 lines. I could take the x values and average them, or I could do all these things. But I got 2 points. That defines a line. Here you go. Remember, still parametric. Right? And then you say, I want the midpoint between those two points. You have the foresight to say, actually, it's not called midpoints in Grasshopper, it's called points on a curve. This is just the stuff that you have someone, you need to text me on Skype, hey, what is this? Or ask them all, like someone will know. And then you got the midpoint. So if I turn on red mode, you can see this is all just sacrificial stuff. It doesn't matter, and it's just helping us get to our end game. Who was saying before we need to move, right? Now we can do the move. So we take that geometry, move it in the Y. I think the important part of all of this, and you'll get good at it as long as you're drawing, is thinking ahead, is putting the cart before the horse and saying, what is it that I want to get done? So as you can see, it's not actually just this grand scheme of things, it's actually along the way, you're almost working yourself step by step backwards to the solution. Hey, how do I define this point right here? I probably need another subroutine to get me there. All week this week, you're going to see, it's always thinking backwards. What is my final thing? It's about thinking of things in a new way. It's about breaking things down to their core rules rather than just, okay, 3 points done. It's about letting yourself be available later. And then I'm sure most of you know 3-point arc. In fact, let me demonstrate something. So I got 3 points here, right? points. 1, 2, 3. Good. All right. 1, 2, 3. Let's see what happens if I put those in. If anybody's done computer scripting or even Excel knows when it looks red or orange, it's never a good thing, and it probably means like, you know, you'll look at this, collinear points result in a, I don't care, I don't know what that means, can you just tell me what to do, and it's always some cryptic error. In this case, it's always beautiful because this is called, I call it visual debugging. Rob May had taught me that term, and I think it's a beautiful term. It's literally being able to look at the problem, a little picture, and know, what's the problem, guys? What's the problem with this picture that we're trying to do here? Why is this thing orange? It's a line, yeah. We can't actually use this component because mathematics doesn't allow us to. So if I actually use this one, not really what we were looking for either. Why? It's because it's in the wrong order. So, okay, let's go. 1, 2, and where's my head? Bada bing. And now, every time the architect wants to change your arc, you got it. It's not going to be as nice as drawing it by hand, but it's ready to be changed at the drop of a hat. I chose this problem first 4 years ago because I was really interested in seeing if a computer could determine the best arc for structural loading. So just letting it bounce around and figure out the best almost funicular shape of the curve. Obviously I used more parameters than this, but that's where I started. And it would be nice if, just based on this, you're not doing anything really complicated, you're not dealing with data trees, you're just dealing with lists of geometry. And everybody else start to think now, okay, how does this affect me? What does this problem show me that I could work on now? So there's our arc, completely parametrically defined via this, okay? And there's nothing in here that is hard to understand. It literally is, if I pull out a panel, most of you know, I can just look at this and be like, okay, like there's data. It's just lists of data. Right now there's no list because we're dealing with one thing at a time. So that's why I have another example which we're going to talk about today and tomorrow. So, what did we have to do? We needed to determine in all of the freeform zone, which is what you're seeing here. I can't really zoom out because this computer isn't so powerful. We had, along any given member on a section, I'm going to draw it weird, some sort of architectural envelope, and awkwardly placed in there, a structural member. Don't worry, it's just geometry we're going to talk about. We're not going to talk about the structure. So you guys can imagine, we were told we need to be able to be within a certain tolerance of this line and this line that the architect gave. And here's our member. This is just geometry, we're not talking about structures. But our geometry is already defined, as you can see. It's just black geometry right here. Zoom in a little bit more. Okay, so there's the black geometry, and you can see the purple geometry goes around it. The purple is what I've drawn in red up here, and that's all you have now. It doesn't matter anymore how it was set out. All you have now is a geometry problem. Where on these members is it that we deem a clash? So we had to go through and actually investigate in 3D for all of these members. I think what a good exercise is for everybody going forward, and I think afterwards what I did in Hong Kong is I just issued one of these members and I let them use it as a quote-unquote homework problem. So you would have the exact same inputs that I did going forward, and you could try to determine how to make the tool that I'm about to demonstrate. So let's look at this a little bit closer. So as I said, mess, absolute mess of geometry, and you got to be able to make sense of all of this. So the first thing that you would likely like to do is at least be able to inspect each member. Like get this type of picture to understand at each level how is this actually looking. Like to us that's a mess. You can't actually make sense of that. And for those of you who use 3D CAD or Rhino, you know how much of a pain it is even to measure along the length of that in 3D, how close you are. It's almost impossible. And we had to do it for all these hundreds of members. So what was the first stop on this? Let's see here. Let's isolate some geometry. All right, that's better. Don't worry about the points right now. That's those. So, here, I got my architectural envelope here. I got what Bureau Happel just says the member should look like, and somewhere over here I have a center line. London center lines. One curve is in there. So that curve I took to be the basis of what we're going to use, all right? So what we can do, I'll show you how the tool works, then we'll explain it. Grasshopper. So set one curve. All the other information has been put in here. So all the other geometric information for the architectural envelope, for the 3D geometry has been put in there. And what I wanted was a tool that could go through, I picked a really bad example. Let's see if we can find a better one. I wanted this as a picture. I wanted to just be able to take my slider and see along it. It's hard to see on this one because it's not that bespoke, but you can see as you go, our member goes through. Our member is relatively straight in comparison to the envelope. The member is warping around it and those values are changing. So this is step number one, is to be able to use essentially lists of data to create something like this, a nice visualization tool. Remember, the end game for us, this was just a nice little checking, nice little extra tool. We need to be able to do this on steroids. We need to be able to do this for hundreds of members, for hundreds of points along the members. But you got to learn how to walk before you can run. So, anybody think right now, can anybody tell me how on earth I went from poly surfaces, from the architect, poly surfaces from Bureau Happel, a line to this image right here? Does anybody have any ideas?
Data.
Data trees? Nope. No data trees in what you're seeing here yet. Tomorrow we'll talk about data trees. Remember, I got 3D information. Now I got 2D information presented here with you. Don't worry about the dimensions and stuff. We'll deal with that later. Actually getting this picture up. And remember, this picture, this is exactly like you did before. You draw this, that's one thing. This time this took me 1 second. This took me 10 seconds now. So we're 10 times as much to draw the picture. And now, just like before, you could draw any arc you wanted. Good luck drawing 10 seconds at a time all of these profiles. I beat you every time at that one just because I scripted this. So how did we do that? We needed to do it, and then it was how. Does anybody have any ideas?
You took the center lines of the architects. If the four nodes, any four nodes will make one quadrilateral. So that will be your this plan.
Okay. So I took the center line from the architect.
Yes.
And the 4 points came from
Wherever that center lines are getting connected, you will have one node.
one structural node,
One
where all the
structural
things come
node,
together.
yeah.
But remember, we're not actually looking, let me pull this up. We're not caring about the nodes on this one. We're caring about along the members. I think you know that we did a lot of the node design, right? We're talking about actually the members. So look at the left and right as I go through.
You're doing the sections actually.
Bingo. So right away, those of you who know 3D CAD, I just asked you, can you please go in here and tell me at halfway point what this picture looks like? The first thing you would do is create a perpendicular plane, intersect some geometry, and then actually play in 2D. CAD software, as powerful as it is, we don't play actually in 3D. We play 2D planes at a time, which is why Grasshopper or Rhino always has the isometric view plus elevation, plan, and section. It's just easier to work that way. So in this way, Samir is right. We knew right away that at the heart of this, you needed to take a section. So let me just step through the script to show you guys exactly what's going on one step at a time, because this is also a very valuable skill. So, green mode. When you're scripting, use green mode and click through as you go. So what comes down? A mesh. What does that mesh look like? Mesh, architect's mesh. Green mode, going to try and show us the center line here. That's the center line. What do we do here? Let's see here, 0 and 1. That's that point on curve thing you showed me before, right, Medio? So what I did was I took the curve and I just made it a straight line. This is for reasons that we won't get into here. This was remember I was talking about subroutines of subroutines. This was for reasons that come when you have members that are like this and stuff like that. It really becomes more important to scrub your geometry, which is what we're dealing with right now in Swan is you always have to scrub your geometry. We're going to deal with this part of the script on Thursday. It's a really important part. It's about geometric searches. Let's not worry about that right now. What is important is, along that member, I create this perpendicular frame. All right, so perpendicular frame is a really important one to know. It's just exactly what it sounds like. It's along your member perpendicular. And we knew that was going to happen. Create a plane surface. Okay, that's fine. And there's the intersection that Samir's been talking about. That one is in between our geometry and that plane. And then there's another one here between the architect's geometry and that plane. And the important part to know right now is if I hover over one of the outputs, we know it's just a list. There's nothing fancy going on here. It's a list of 4 lines. It's a list of 2 polylines, so it's 8 curves, right? Because this one's a solid rectangle or solid section. And then that's it. I mean, we actually have exactly what we've been asking for, the dimensions and stuff. That's a game we'll play on Thursday because that involves a little bit of a higher order analysis. The only other thing we do here is we say, hey, would be great is that picture right there isn't too useful to us. It doesn't really help us. It's in 3D. We don't like that. Can we have that as a viewer somewhere? And the answer is yes. You use something called the orient tool. Once again, it's just a list going in, and you tell it, please convert this geometry from one space to another. So the space that you're in right now is the plane that you created. The other plane is XY. And sure enough, brings it over. And then we play some games here. I don't want to talk about them today because they are a little bit, they're not hard. They're just for Thursday. All right, let's leave it at that. But that's just, all of this game right here is just for us to be able to pick out the right points in that mess right there and create dimensions. Okay? That's all. That's all the only games we played. And right away, you can see, we went from parametric arc, we saved 1 second each time. On this one, we saved 10 seconds each time. And remember, we had hundreds of members with dozens of points on each member that needed to be drawn. So instantly, you can already start doing the math, how much work this was worth. Do you even realize that for even this conversation right here, when we were doing it, the conversation of how do you define close starts to matter. If the facade brackets are coming out perpendicular to the member, it's different than Euclidean geometry, which says the closest point from here to here is a perpendicular line on here. One is perpendicularity here, one is perpendicularity here. It matters. The first time we sat down, another key principle of this is this morning with Shival and Vimal, we're talking about Swan Lam. Geometry is important, sure, but information is even more important. First meeting we sat down under these tight conditions, we literally kind of just sat down and said, we have to come back or reschedule. Because every single party, the contractor, the facade contractor, as well as us, we're using different information. So some of us had different information for this stuff, this stuff was different, center lines were different, it's a mess. It really becomes important that you understand that if the beginning of my script is something that's called curve, when I right click and say reference it to something else, what you reference it to better be the right thing. And we've had this conversation this morning for Swan Lung, and as you can see on this one, normally we go and we say, oh, somewhere in there there's a file to reference from the architect. We don't change the name of it, right? But it's not right there. It's somewhere behind the scenes. On this one right here, that's Zaha's nomenclature. This is our nomenclature. That's literally what's in the contract documents. And that way, there's nobody who can argue with you. It's like, I'm using the geometry, I'm not changing it at all, I'm just extracting data from it. And that's lists and basic scripting. If you guys watched the guy from that one conference, I sent out that link. Very inspirational stuff, because with this tool at your helm, what we didn't show here today, but we will, is it gives you a lot more power to like sort of see things that you never thought possible before, because you can only think of so much at once. But when you have this, you can really start to break down what is a very complex and messy situation to its nuts and bolts. And maybe if this was still designed, and we were the facade contractor, we could actually use this tool to actually come up with something very intuitive. So, I think we got 10 minutes for some questions, and then tomorrow we'll talk about data collection. So, any questions?
How this was converted into drawings, normal working drawings?
So, for
For the
this,
contractor to execute?
for this specific instance. So what we did for City of Dreams was we knew that with the complexity of that freeform area, which you saw, we would never get away with doing your typical leisurely thing on our jobs where architect works in 3D, gives us 2D. We take that back to 3D, we give the contractor 2D. 3D back and forth, back and forth. This wasted resource, this friction could not happen with something as disgusting looking as that. So we agreed with the client a long time ago that we would deliver 3D information. The members themselves were set out via centerline models that had just the center lines of the members, as well as an orthogonal vector that defined the orientation of it. So all of these are planar curves, so it could be done that way. For the node design, which a lot of you might know, the structures guys especially, that one was, the deliverable was all 3D polysurface plate design. So it went out that way. So there was no 2D drawings. There was two details on how to put it together, but the actual setting out was three-dimensional. And you couldn't do that had you not had something that allowed you to quickly, rapidly spit 3D information. At the guts of that three-point arc example, I know it's not necessarily the most interesting one, it's not the most useful one, but that is the guts of what's here in front of you and what made City of Dreams, XRL, a lot of these projects in Bath and London, that's what it is. Is that a nice question? And eventually, I mean, this morning, Siobhan was telling me that you guys are actually delivering 3D information on some projects already, like the Revit models. So, I mean, this is, I think eventually clients will catch on that doing this 2D dance is costing them money. And to push something across in 3D is going to be necessary. And the thing is if you're only passing on Revit, that works for most buildings, but it won't work for every building. Especially technicians in the room know. Revit has multiple shortcomings. It's not a perfect tool. It's just there for your bulk of the buildings.
So when the geometry came in from Zaha for this particular project, did it have any mathematical form or is completely abstract?
If you look online for the first rendering from Zaha's, as far as the exoskeleton goes, I wish I had a picture of City of Dreams. So does everybody here know City of Dreams?
Yeah.
Okay, just to be clear. It looked like, Spider-Man when he shoots a web, it just looked ridiculous. Like it looks awesome, don't get me wrong, but as far as the structural engineering goes, like, there's no vertical lines on there. It had no rationale. So I think what they did in London, I think Wolf was over there, he rationalized it a bit to make sure that we did have proper load paths and whatnot. But in what you're seeing right here, it's going to be hard for me to zoom in on it. Let's try. When you talk about the actual detail of the nitty-gritty, which is what we've been going on and on about for a couple years now with City of Dreams and the connection design of the exoskeleton. It was so important, so special because of this picture right here, because you can rationalize these members, before they were, warping, or they could have been warping, or whatever. We rationalized those members internally in London to make sure that it was a planar curve, so it was easier to fabricate. But that's the reason why, as you sweep through this thing, these values are changing, which makes it a lot more difficult. The difficulty comes out now in the facade brackets rather than the member. That's okay, they can handle that.
So it's a planar curve. I mean, the members are
All of
in
them are
one
in
plane.
Yeah.
One plane curve.
And then the only issue is you push some difficulty away from the fabricator for the members, you push it to the fabricator for the facade brackets, and then you push a lot of difficulty for what happens right here. So it's just about managing, hey, where's the best cap?
So every node is a planar node, or it could be non-planar as well.
The nodes are a different story. The members themselves, all of them can be taken and just laid on the ground flat in one way, shape, or form. So they're all, some of them are like this literally, but you can take them and put them on the ground. They're flat. So at least two of their sides are planar if they're an SH, a square hollow section. So that drastically helps the fabrication, but for the nodes, that's a different story. That's what you see on the screen right there.
For designing, like, how do you combine and do all this like?
So all this data that we see on the screen here, right? So, like we said, we have these extruded sections, which was another script. Remember, all we issued contractually was lines. So you gave them a 3D line, and you gave them a plane, basically, and a section in a table somewhere. So we had to first say, contractually, what is it 3D that we have? We actually didn't know at first. Like, there was no central file that said, hey, this is what we're actually issuing, because we issued it like kind of typically, just said, hey, sections, and also this is a little bit to help you set it out. First thing you do then is come out there, you draw that business, right? You extrude it along, and that's how you see the black. So first you get that up there. The center lines came from London, but we had to process those a bit, as you saw already, to make it work with this particular script. Little detail stuff, nothing to worry about. And then there's Zaha's, right? And your question is how do you manage all of that? Like I said, first of all, the important thing is you know that this is the law. So everybody in their report is going to say, we are using 1760_20A XO whatever for Zaha's information. That's law. And then you lock it. So you can see it's grayed out here because you're not allowed to touch it. And then, literally, it's exactly like the parametric arc. You see it right here. Zaha's information, our centerline information, our information, exactly how it looks on, we were using EGNX, so all the information was on EGNX. So no one could say, Bureau Happold, you're using old information. And then from there, which we will talk about in due time. Tomorrow is going to be, the big difference between tomorrow and today is this, is all those brackets right there. Those brackets mean increased productivity. You're doing things multiple times. So tomorrow what I hope to get into is saying, great, I don't expect everybody to spend here all night trying to do a sweeper, but if you're at lunch or something and you want to try something, try and make a sweeper. Like, it's not that hard. You can just see if you can intersect something and transform its geometry to somewhere else. Tomorrow will be the interesting day because tomorrow is where the money is. You might have just saved 10 seconds per time. Now we're going to save 10 seconds per time for 1,200 times. And that's really where it starts to become, wow, you're on a different level. But baby steps. If you get down this stuff that we talked about today, you're 60% parametrically fluent and you're crushing it.